Okay, so with correlation, the big picture here is that we have these descriptives, frequencies, and assumptions, and then those are the very first things that we do, and so that's what we've been doing. Is the first thing that you always have to do anytime that you have a data set is to run the descriptives, just so that you can understand what you even have. So some of you did that on Module 3, and some of you did not. So you need to make sure that you're doing that every time from now on, so that you know the minimum and the maximum of blood pressure or cholesterol or whatever you're using, and then the mean of that. And so that way you can at least understand if you have, if your mean is 40 and most of your values are under 40, but you have a couple of outliers, that tells you a lot about your data. So the descriptives are super, super important. And then your assumptions you have to do, because you have to know if you have parametric or non-parametric data. So the next step is correlation. And so that's what I was really talking about, how cool correlation is, because it's just the basis of all of the other tests. And a lot of times people run correlations just as kind of a documentation thing, because it helps you really get a grasp on if there's relationships at all. If there's no relationships, then there's no purpose in doing a lot of the other tests. So inferential statistics and descriptive statistics. Inferential statistics are things that you want to infer. And descriptive statistics just simply describe what's going on. So if you think back to like a research methods class, your descriptive correlational, your comparative descriptive designs, all of those designs are going to use descriptive data techniques, like frequencies, mean, median, mode, those types of things. Inferential statistics are where you can make a little bit more conclusions, and so like with inferential and descriptive, inferential is always more complex because you're actually trying to infer something from the data that you have. And so with your correlations, you have to think about a relationship between or among different variables. You have to make sure that all of your data are from a single population, and you can use a Kramer's V, a Spearman's rank, or a Pearson's R. And so what we're going to use is a Pearson's correlation test, because we're going to use interval and ratio data for this. So with a correlational analysis, you're getting a linear relationship, and what you can look at is the strength of the relationship. And so one thing that I hope that you took away from a research methods class is that correlation is not causation. So just because you have a relationship doesn't mean that one thing causes another, because there could be a relationship between the times that I drink milk and if it's a full moon. But that's me drinking milk doesn't cause the moon to be full. So there's a total disconnect between the way people understand correlation and causation. A lot of times in news articles, you'll see people trying to make causation from correlation, and that is not the purpose at all of correlation. So like also in your research methods class, when we talked about the different stages or the different levels of measurement, and what we talked about at the beginning of this class too, interval level is the strongest level. It's the highest level that you can collect data, and it's data that has a true zero. And so anything that we want to do, we want to use at the interval and ratio level, because it's continuous data. The continuous data is going to give us the most information. And so what we want to use when we have a bivariate analysis is a Pearson's product moment correlation coefficient. And so the Pearson correlation coefficient is what it's typically called, and the R is called the R value, and that's your correlation coefficient. That R value tells you the strength of the relationship. So if you are going to use the Pearson's product moment correlation coefficient to tell you anything about your data, your bivariate data, then you have to know that you are using interval or ratio measures. You have to have normal distribution of at least one variable. You have to have independence of observational pairs so that one doesn't rely on the other, because if you have one that relies on the other, then obviously they're going to be related because they rely on each other. And then you have to have homoscedasticity, which is where you have a linear relationship where there's enough data dispersed above and below the regression line to give you equal variance, so that you're not looking at invariant data. So the analysis techniques that we can use are always based on the data that we have available. So we're going to make some assumptions about this data and say that we have high-level measurement, interval or ratio, and is normally distributed, independently observed, and homoscedastic. So you have to test those assumptions. So the Pearson's R, this is a pretty good video about the Pearson's product moment correlation coefficient. Again, those assumptions, you have to test for your assumptions before you can actually run your correlation. So you need to look for interval measurement of both variables, interval or ratio, a normal distribution of at least one variable. So if not all of the variables are normally distributed, that's okay, but you at least need one that's normally distributed, independence of observations, and homoscedasticity. So with your results, when you get your R value, a value of -1 is a perfect negative inverse correlation. So if I'm talking about an inverse correlation, that's going to be as one thing goes up, another one, I guess I have to pick another line, another one comes down. So that's inverse. If I'm talking about a positive correlation, that means as one goes up, the other goes up. If I get a 0, that means they are completely unrelated. And so what the range is a -1 to a +1, and I can have any value in between -1 and +1. So now I'm going to say, all right, I have my value. If it's between -0.3 and +0.3, I have a weak linear relationship. If I have -0.5 to -0.3 or +0.3 to +0.5, then I have a moderate linear relationship. If I have anything less than -0.05 or greater than 0.5 up to a -1 or a +1, then I'm going to have a very strong relationship. So you're looking at the R value, which is the correlation coefficient, to tell you how strong your relationship is. And so this would be no relationship. So you see right here at the top, let me see if I can circle this, your R is 0.0. And so that 0 is going to tell you that there's absolutely no relationship between all these data points. And you can see it visually. There's no discernible pattern. So if I have a 0.5 and I go back and I look over here, so my 0.5 is a strong linear relationship, I see that strong linear relationship. There is a method there to those dots where it's showing you that one thing is related to another. And then a -0.5 is that inverse relationship, so you can see that your line is going the opposite direction. And so when you think about the strength of a linear relationship, the actual strength of the relationship, like in nature, in its normal setting, is what your linear relationship statistically will reflect. What correlational test you use, because if you have ordinal data and you use an interval measure, you're not going to get good results. And how many data points are used, or what is your sample size? So if your results are weak, you have to think about if there really is a relationship, or if you didn't have the right measurement tools or instruments. So if I'm measuring IQ and I give somebody the RD exam, that's not going to measure their IQ. It's going to measure if they're competent at being a registered dietitian, which isn't equivalent to IQ. And so the measurement wouldn't be precise. And then the correct correlational test, so which statistical test, and it could have been incorrect test. And then the sample size, because maybe a type 2 error occurred because I didn't have the sample size that I needed. So as you write your conclusions, for your module, you really need to be thinking through these questions, because this will help you explain your results. So I would highlight these questions, and if you have insignificant or results opposite to what you would imagine, go back to these questions and make these points that you talk through in your conclusions. When we think about relationships, a positive relationship is when one score is high, the other score is high, or when one score is low, the other score is low. So, you know, I think about the amount of physical activity and heart rate. So as you do more physical activity, your heart rate increases. Yeah, in the moment. And so you would have to be very specific about your conceptual and operational definitions. And then in a negative linear relationship, when one score is high, the other is low. So, for example, if I'm looking at the relationship between physical activity and body weight, and I get the results that as physical activity increases, body weight increases, that's a positive relationship that I wouldn't expect. But maybe if physical activity increases and body weight decreases, that's a negative linear relationship. And that would be something more that I would expect. And so, like I said before, these are those values that you're comparing your R to. So the possible values are anything between -1 and +1, but you're looking for the weak, moderate, or strong relationships. So a very small relationship is shown here because that line is not very strong. A positive relationship is shown here, and it's a very strong relationship, or at least moderately strong relationship, because just of the linear trend of that line, how steep the line is. And then this is a negative relationship, or inverse, because as one increases, the other decreases. So if I'm looking at this chart, I want to know which one of these tables would I be most uncertain about a relationship being significant. So here, I'm pretty sure that this is going to be significant because they're clustered along this line without me even having to do anything. So I'm certain of that one. This one I'm pretty certain of. Let me go back to where you can't see. This one I'm certain of because there is no relationship. It's weird, right? And I'm using a Pearson's test for a ordinal set of data. So that just doesn't make sense. This one is where I would be the most confused because it's all over the place. Like there isn't a discernible trend. And so this significance point is super, super important. So you can have you can have a really great R value. Like maybe I have an R value of 0.9. But if my significance level, which is my p-value, it should be less than 0.05. If my p-value is not significant, then the R value doesn't even get talked about. The first thing that you have to look at is your p-value, your significance. And so you look at the significance and then the coefficient. If your significance is not significant, then there's no point in you even discussing the results because there's nothing there. And as far as I'm concerned with results, it's like being pregnant. Either you are or you aren't. You're either significant or you're not. You're not somewhat significant because there's a fine, like that line of p equals 0.05 is definitive. And so either you're above it or you're below it. You're not in between. So you're either significant or you're not. And so if you're not significant, then you don't even talk like you were or that you were even close. So then with a bivariate correlation, we want to use our Spearman rank order correlation coefficient, and that's where we get when you can't use a Pearson's. And so this is a non-parametric test. You would use a Spearman rank order. And then Spearman rho is is the test variable that you get, which is also an R value. You can use Kendall's tau. That's a non-parametric test also, and the result is that you get a Kendall's tau value that is like your R value. So this is something that I just think is really, really cool about the output that you're going to get from SPSS. So you get this diagonal line right through the middle of your table, and you see that there's these ones. So marital status to marital status is perfectly correlated because it's the exact same variable. School level to school level, again, perfectly correlated because it's the exact same variable. So you see that down the matrix. And so what you get is this on the bottom and this in the top are exact mirror images of one another. So what I usually do is just totally black out everything on the bottom and only look at the top so I don't get confused because it's the same information. It's a mirror image. So when you get your correlational table, this is what it should look like because I'm going to ask you to do all your variables in one table just because it's so much easier to look at. So you can completely ignore either half because it's the diagonal line down the matrix separates it. And so in your output, you're going to have 4 cells like in this matrix. You only had 2 variables. You're looking at the relationship between BMI and weight. There's only one correlation coefficient of interest because even though you have 1, 2, 3, 4 boxes, these 2 boxes that are on your diagonal are the same information. It's the 0.911, which is your Pearson's correlation, and since there's only two variables, these are mirror images of each other also. So you only have 0.911 as your correlation coefficient, which is super strong, right? And you would expect that because weight is a function of BMI. You have to have weight to calculate a BMI. And so if they weren't related, you would know that you calculated something wrong. And so the Pearson's correlation that's listed right here is really your R value. The significance that's listed here is your p-value. So you need to make sure that when you're reporting your statistics, you're using the APA format where you have your R value and your p-value both in your parentheses. And so in this one, there's 25 cells in this matrix, but only 10 of the correlation coefficients that I'm going to even look at, because we talked about this diagonal line. So if I'm going to look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes, well, there's really only 5 of interest because they're the ones that have significance. And so SPSS automatically flags with the asterisk the significance. And if it's 1 asterisk, it's 0.05. If it's 2 asterisks, it's 0.01. But in your results section, if it gives you the actual p-value that's 0.017, you put 0.017. The only time you put p equals less than 0.01 is if it doesn't give you the exact value, like the 0.000. The only ones I'm interested in are the ones that have the asterisk beside the R value, because now I know they're significant. Like I said before, if it's not, it can have a really great R value, but if it's not significant, it doesn't mean anything. And this is 0.05. It's not significant because, like I said before, either you are or you aren't. 0.05 is not less than 0.05. It is 0.05. So it's not counted as being significant. So this goes back to that idea of correlation and causation. So this is from our data set, and I could say waist circumference is significantly, or BMI is significantly related to hair color, right? Because that my p-value is less than 0.05. So like body fat mass is related to hair color. It's statistically significant, but it's useless information because it doesn't have anything to do with hair color. And it wasn't my research question. So be very careful as you're doing these analyses that you're not looking at correlations that are spurious. So correlation does not demonstrate causality. So this is an example of where hormone replacement therapy had lower than average incidence of coronary heart disease, and so doctors thought that HRT was protective against coronary heart disease, and so they started doing randomized controlled trials, which are the gold standard of research, and they figured out that people that were taking hormone replacement therapy just had generally healthier lifestyles, and so it really wasn't related to coronary heart disease at all. And so this is an example from your textbook where you have anxiety and exam performance. You have 103 students and time spent revising homework, exam performance, exam anxiety, and gender. And so what you look for, the first thing you do is you check your assumptions, and if you have linearity and normality, then you can look at your graphs and your scatter plots. And so to tell you more information. And then once you realize that you have assumptions that are met, then you can do your Pearson's R. If you have assumptions that are not met, you have to do a Spearman R or a Kendall's Tau. So when we go into correlations, these are the step-by-step instructions, and I'll go through in just a minute through SPSS with our data set. So I'm going to click through some of these. This is an output that you'll get for the Pearson's correlation, and so this looks a little bit different than what I'll ask you to get. And so this is an example of an APA-style correlation table. And so pay particular attention to that because I'm going to ask you to make sure that you have correlation tables in your module write-up. So again, it varies. The R value can vary between -1 and +1. It has an effect size of small, medium, or large, and your R square is your coefficient of determination that helps you get to your effect size. So Sometimes there's a third variable problem, because if you're looking at a correlation between two things, maybe there's a third variable out there that's accounting for all the difference, and so you just didn't identify it, or you haven't identified it yet. So it looks like there's no relationship between the two variables that you have, when in actuality there is, but it's just part of another relationship. And so with non-parametric correlations, you use your Spearman's rho or your Kendall's tau. And this is the output that you would get for the Spearman's rho. And so you're still going to look at your significance value, and you're going to look at your correlation coefficients. The Kendall's tau, again, you look at your significance value and your correlation coefficient, which is the tau. And so the difference between the rho and the tau is the way it functions in SPSS mathematically, but also the way that you write it up in your results, because you would actually show the Greek letter rho or tau as your correlation coefficient. And then a partial correlation is where we do account for that third variable and the effect that it has on both of the other variables that we're looking at. And then a semi-partial correlation is where we look at this third variable, but we control it based on the other two. We're not doing partial or semi-partial correlation. We're doing bivariate. So this is just an example. You need to know what it is, but we're not going to actually conduct it. So in this example, I know that I have some anxiety and some level of performance. And so what is accounted for here is only 19.4%. But if I add in revision time, then I'm getting more and more specific. And so I can look at the exact variance that I have for the revision time, anxiety, and performance. And so a partial correlation is where you're looking at all three of them related together. A semi-partial correlation is where you're controlling, for example, revision on exam and anxiety. And so you're not looking at all three of them together. You're looking at the effect that maybe revision would have on exam anxiety. So partial correlation, you do need to have this information in the back of your mind, but knowing that we're not going to do these. So your conclusions with correlation is that it's one of the most common forms of data analysis. It's definitely the easiest. It's a lot of fun because you could just throw everything into a matrix and have a great time interpreting it. But what you have to know about it is that you have to do your assumptions testing, and then when you get a result, it's going to be an R value and a P value. Your R value is your correlation coefficient that tells you the strength of the relationship. So what you're going to do for your assignment M4 is you're going to put all of these, so you have three different things I want you to look at: money spent on carry-out and BMI, BMI and minutes sedentary activity, total cholesterol, and blood pressure. So it's 1, 2, 3, 4, 5 different variables, because BMI and BMI are the same variable. So it's 5 different variables, but you're looking at 3 different comparisons. And so here's our step-by-step example. I'm going to go on over to SPSS, and we're going to look at age and BMI. Okay, so I'm going to analyze, and I'm skipping the assumptions part. I'm just going straight into doing the correlation. You should know how to do the assumptions for linearity, normality, and homoscedasticity. So I also would have already expected you to get your descriptive statistics. You need to get your, so if we go, let's actually go back to this PowerPoint. So if these are the variables that I know that I'm assigned to use, and I know that I'm assigned to do the Pearson's correlation coefficient, and I can only use interval or ratio data. So that tells me right off I'm not going to have any categorical data. So I don't need to do frequencies because I'm not going to have categories to look at. But what might help me, though, is if I come back over here to my SPSS, and if I wanted to do frequencies, then oh, let me pull SPSS. Okay, here we go. So if I'm doing a frequency, I don't want to do it on a continuous variable because it's going to tell me one person has a BMI of 24, one person has a BMI of 25, 26, 27, 28, on and on and on. It's useless. But what I do want is how many people do I have that are male or female? How many people are Hispanic or not? What school level have they completed? Are these people married? What's their income? So these are all categoricals. And so I want those frequency tables so that when I write up my descriptive information in my results section, I can say that the majority of the sample was female. There's 182 females and 87 males. The majority of the population was non-Hispanic white, and that most people had completed either some college or a college degree. So this information is super important for you to be able to just describe your population, your sample, and tell me that you know a little bit about the people that are behind these numbers. And so then when I'm going to do my my descriptives is when I can use all of my continuous information. So I want to know the average age. I want to know the average BMI at 0. I want to know the average systolic blood pressure and maybe total cholesterol. And then what was the other? So we got age and BMI in there. So I'm going to want to know the averages for all of my variables that I'm using in my analysis. And I also want to know the minimum and the maximum. And I can get my skewness and kurtosis here. So now I have my descriptives table that tells me that the average age was 36 and the average BMI was 35. The average systolic blood pressure was 126, and so you should know, is that high or low? And then the total cholesterol, the average was 177. But now I can also tell you that the minimum age was 18 and the maximum was 80. The minimum BMI was 17 and the maximum was 64. So that's a lot of variation there. So just these frequencies and descriptives give me a lot of information. Okay, sidebar. Now let's get back to our correlation. So I'm going to go to correlate. We said we're only doing bivariate, and I want to do age and body mass index. So I know that I'm using a Pearson's because even if it was non-parametric, I'm telling you as your instructor that you're only going to use Pearson's for this assignment. And I want it to flag my significant correlations because it makes it easy on me when I see asterisks that tell me where things are significant. And I want it to be two-tailed because I don't have a hypothesis that either one of these is going to do anything. It is helpful to go in and get your means and standard deviations, so I'm going to continue there. I don't care about the style. I just want it the way that it comes out in the output. So now I'm going to hit OK, and it gives me my descriptive statistics. So if my age in years, the mean is 36.44, I should come back up here, and it should be the exact same information. But correlations is what I'm really interested in. So this is the example that we looked at in the PowerPoint where I have these 4 boxes, but really only one box is important because these 3 are just duplicate information. So I don't have a significant relationship. I have a p-value of 0.240, which is a lot greater than 0.05, and I don't care what my Pearson's correlation is because it isn't significant. So let's get back over here. And so, again, step by step, bivariate correlation. I'm going to move my age and BMI. I'm going to use Pearson's and a two-tailed test. I want my means and standard deviations. And so now I'm telling it's not significant, so it doesn't matter. So I want to go back and look at my data, like visually see what's going on. And so I'm going to get my scatter plot, a simple scatter plot. I'm going to pull my body mass index and my age over so that I can look at my scatters, and I see my body mass index and my age. So my 20-ish year olds have crazy variation in their BMIs, but there's a cluster of people around that 20-year-old age mark, which tells me that that's why my average age was 36, because I also have a cluster around 45, so I'm averaging a 30-year-old. So if I want to add my fit line, this is going to give me a regression line that gives me the exact, or the trend line, to tell me the average of the data points. And so you can see from this line right here that there isn't anything going on. This fit line or this trend line shows me no trend. And that's why I don't have a significant value. So for your assignment, I want you to run your own analysis. And so like I was saying I want you to put everything into one correlation matrix. It's just easier to read that way. But you're going to look at these three different, so you'll have three different paragraphs. You'll have your money spent on carry-out and BMI paragraph, your BMI and minutes sedentary activity paragraph, and your total cholesterol and BP paragraph. So remember that I want you to get the entire matrix, but it has this diagonal line that gives you mirror images, so you only need to be looking at one side of that table. So if I go back to SPSS, let's go back over here and let's just analyze, let's just take a look. So maybe I want to look at systolic blood pressure along with total cholesterol and the hours I watch TV and maybe the hours I use computer. So now I have 1, 2, 3, 4, 5, 6 variables in there, and I'm going to use Pearson's, and I want my correlations tagged. I also want my means and standard deviations. So it gives me this correlation chart, and so see that diagonal line there? So I'm going to look at the bottom. I see systolic blood pressure and age is related, systolic blood pressure and body mass index, hours of computer use, and systolic blood pressure. So there's some interesting stuff there. So this one, it's significant at 0.023, and my R value is 0.165, which is pretty weak relationship. With my systolic blood pressure and my body mass index, my significance level is 0.001, so that's really low. So I have a little bit of a stronger relationship there. It's very not common to get really strong relationships unless they're related, like the example that I showed you where we looked at weight and body mass index, because weight is a function of body mass index. All right, so that wraps up the lecture for Module 5, and SPSS, we went through that.